Hi, everyone. In this lecture, we're going to discuss the k-nearest neighbor, and specifically, we're going to discuss the basics behind how the classifier is formulated and how the classifier works. And we're also going to present an example with which we can solve using the KNN. So in this specific example that we had discussed in one of our previous classes, we wanted to recognize among three types of flowers, namely Setosa, versicolor, and virginica. And the features that we used for this classification task were the widths and the lengths of the petal and the sepal of each flower. So then here is some of the data that had been used in order to train a machine learning classifier that can recognize among these three types of flowers. And here we can see a visual inspection of the data. So after visualizing our features, we were able to obtain a better intuition about the data. Namely, we were able to better understand the distribution of each of the features, as well as to understand the scatter within classes and the differences across classes when we plotted the 2D scatter plots that represent pairwise combinations of features. So in this example scatter plot that we specifically identified because we saw that there is a high differentiation among the three classes, the x-axis is the petal width and the y-axis is the sepal length. So our training data are being reflected here with three different colors. Namely, we're using the color red for Setosa, the color green for versicolor, and the color blue for virginica. And we see that there is some type of clear distinction among the three colors given the training data. And this potentially indicates that these two features will be able to effectively differentiate among the three classes for unknown examples as well. So if we use a k-nearest neighbor classifier in order to classify among the three classes, let's say that we have a test sample that is depicted here in the uncolored circle. What KNN will do is that the gist of KNN is that it will try to see the classes of the nearest neighbors of this test sample. And then it's going to assign this test sample according to the classes of its nearest neighbors. So here is a representation of the data that we usually get when we have any machine learning task. Usually the data is organized in a table, especially if we have a small number of samples, and each row of the table represents one sample. So this first row here would represent one sample whose sepal length is 5.1, whose sepal width is 3.5, petal length is 1.4, and petal width is 0.02. And the label for this sample would be the Setosa flower. So while the rows represent one sample, the columns represent the features. So the first column, as we get here from the attribute information, corresponds to sepal width. Second column corresponds to sepal width. First column corresponds to sepal length, and so forth and so on. And actually, you can find this data set publicly available from the UCI repository. So if we were to formally a little bit more represent the KNN classifier, let's assume that we have a set of training data and a set of testing data. And the training data can be represented as pairs of samples, x1, y1. x1 represent the features and y1 represent the class. And the same thing can be replicated if we have n training samples, and the collection of our n training samples would actually represent our training set. So the goal of any classifier would be to learn a function that assigns a label y to each training sample and each test sample based on the features that are provided in the input. So the function f has an input x, which are the features, and an input y, which are the labels. Now, while in the training data, we are using the labels in order to learn the classifier. In the testing data, we are using the labels just to evaluate how closely the labels of our test data are with the predicted labels of our classifier. So essentially, the test data are used to assess how well the function f, which does the mapping between the input and the output, can perform in predicting an unseen test sample. And the very important thing here is that the train and the test data should not overlap, because if we have a leak between the two, then the classifier, then we are not able to effectively evaluate the generalizability of our classifier. So we can also have special cases in our classification examples. Let's say if we have a binary classification, the output can have a binary form. Another convention here is that in the input, we will assume that we have D features. So this X will be a D-dimensional vector. And in the output, we will assume that we have C labels. So while the output Y is scalar, so essentially the output Y only consists of a single number, the potential numbers that this output can have are one of the C labels, one of the C classes that are present in our classification problem. So according now to one nearest neighbor, we will assign a test sample to the class of its closest neighboring training sample. And mathematically, how this is represented is that we have this function, this mapping function f, which takes as an input the features of our sample X, and as an output, it produces the class of the nearest neighbor to the test sample X. So how can we find the nearest neighbor to the test sample X, this NN of X? We can compute the distance between the test sample X with all our training samples. In this case, we have computed the Euclidean distance, which is represented by the square of the L2 norm. So after computing the distance between our test sample and all training samples, we find which is the test sample that yields the lowest distance, and that would be the closest neighbor to our test sample. Now, also pay attention here that instead of taking just the minimum of this expression, which would yield the minimum distance between the test sample X and its neighbors, we are taking the arg minimum just because we want to find the index of the training sample that is closest to the test sample. And by finding this index, we are just going to map this index into the label in order to get our final decision. And here, that part of the equation, what it does is that it simply has expressed this L2 norm in another representation. So essentially, it has assumed that each of the vectors X has D elements, and then it has just written this expression in a more analytic form. So if we were to represent this in a visual way, again, given that we have our blue and red classes, and we have our test sample that is not being represented by any color, we find the closest neighbor to this test sample. From this visual representation, we can see that this closest neighbor to the test sample is this red dot. And therefore, after we find that this neighboring sample belongs to the red class, we can also assign our test sample as this belongs to belonging to the red class. So while this is a very intuitive approach and actually a very simple approach, the main drawback behind this approach is that the decision boundaries can be quite noisy, just because we only use one training sample in order to make our final decision. And especially if we have data with a lot of outliers, or if we have a lot of noisy data, this decision can be quite noisy, So what would be the solution for this? The solution for this could be to increase the number of nearest neighbors that we use in order to make our decision. So instead of obtaining our decision for a test sample based on only the first nearest neighbor, we can use multiple nearest neighbors. And in this case, we can use k nearest neighbors, thus the name of the classifier. So let's say that we have found the first nearest neighbor. Now we can do exactly the same thing as we did before in order to find the second nearest neighbor. But instead of looking for all the samples in our training set, we look for the distance between our test sample with the trained samples minus the sample that belongs to the first nearest neighbor, just because this has already been taken into account. We can do the same for the third nearest neighbor. So we compute the distance from the test sample to all training samples that minus the first and the second nearest neighbor, and so forth and so on. So this results in us obtaining a set of k nearest neighbor. Essentially, these are the k training samples that are located closest to our test sample X. So after we have obtained these k closest samples, what we need to do is that we need to examine the labels of each of our training samples and see in which class each of these training samples belongs to, and take a final decision for our test sample. Since we know that it's not always very likely that all our neighbors belong to the same class, we have to find a systematic approach in order to make our final decision for the class of the test sample. And the easiest way to do that would be to vote. So essentially, the easiest way would be to see which is the class that is most represented in each of these k nearest neighbors. So what we need to do is count the number of neighbors that have voted for each class. So for each class, we get a vote. And this I here, this capital I, indicates the indicator function. So if the k nearest neighbor belongs to a target class C, then this target class C gets one more vote. So essentially, this variable, VC, represents the number of votes for the C class, or otherwise, the number of neighbors from this set whose labels are equal to small c. And we do the same for all classes ranging from 1 up to capital C. Now, after we have counted the number of votes for each class, we assign our test sample to the class that corresponds to the highest number of votes. So here, if we were in the same example that we showed before, if we were to see how a 3 nearest neighbor would be applied, we would have our test sample here, and we would find the training samples that are closest to our test sample. And because we are talking about the 3 nearest neighbor, we would find the 3 closest training samples. And after computing the distance of our test sample with all our training samples, we can find that these 3 here are the ones that have the lowest distance, therefore they are the ones that are the closest. We see that from these training samples, 2 out of 3 belong to the red class and 1 belongs to the blue class. Therefore, our test sample will be assigned to the red class. Similarly, if we do the same procedure for 5 nearest neighbors, we see that the blue class gets 3 votes and the red class gets 2 votes. Therefore, our test sample will be assigned to the blue class. And from this example, we also understand how the hyperparameter K, which is the hyperparameter that corresponds to the number of nearest neighbors that are being taken into account in order to make the final decision, we actually understand the importance of this hyperparameter and how much this can change the decisions from one case to another. So in the same token, we can also plot the decision boundaries for each of, for an example of data for different numbers of K. So here we can see the decision boundary when we have 3 classes, red, green, and blue, and K equals 1, K equals 3, and K equals 31. And what we observe is that usually the decision boundaries that correspond to one nearest neighbor are more noisy, and they have smaller regions that can be represented by a class. For example, this smaller green region here, it's being pretty much left all alone among a larger region of red class. However, when we increase the number of nearest neighbors, we see that these smaller regions are kind of being smoothed out and are being more taken into account in the whole context of our data. So a question here would be, what is the computational cost of KNN for labeling a single test sample X, given that we have N training data? And from what we have seen is that we understand that KNN is kind of an expensive classifier. And the reason for that is that for every test sample, we have to compute the distance of every test sample with each of the training samples in order to obtain a decision. So if we have a large number of training samples, this cost would become pretty high quickly. So let's start by approaching this problem by first measuring the cost of computing the distance between one test sample and one training sample. If we are operating on a d-dimensional space, then this cost would be O of d, because we need to compute the distance across each of the d dimensions. Now, since we have now at this point, we have only computed the cost of measuring the distance between each test sample and each training sample, we also need to multiply this by the overall number of training samples, because we need to do this n times, as many times as the number of training samples that we have. So at this point, the cost becomes O of ND. Now, once we have found the distance of our test sample with each of our training samples, we need to find which are the K closest samples, essentially the ones that correspond to the smallest distance, the K samples that correspond to the smallest distance. So the vanilla version for doing that, the easiest version for doing that, is every time to look over the n distances and check and find the first time the smallest distance, the second time the second smallest distance, and so forth and so on. And the cost for this would be O of nk. However, of course, this can be optimized based on all the sorting algorithms that we know. So the total cost of computing, of labeling a test sample, given that we have n training data for KNN, would be the cost of finding this distance, and then the cost of finding the K nearest neighbor. Therefore, if we add these two, this would be O of ND plus NK. Something to pay attention here is that we didn't multiply those two separate costs, O of NK and O of ND, just because one operation followed the other. So there was no interaction essentially between these two operations. So another important thing to keep in mind is that KNN is a non-parametric model, which means that we have not really imposed any structure on our data. We have not really attempted to fit any function in our training data, we have just considered a decision based on the distances between a test sample and its neighbors. And non-parametric models, for the same reason, can be way more flexible. However, they can be computationally very expensive for large data sets, just because we need to keep in memory and we need to compute, to make computations, usually for all our training samples. However, in contrast, we have parametric models for which we impose a structure on our data. Parametric models can be linear perceptron algorithms, for which, for example, we assume that there is only a linear boundary that allows us to classify between classes. And while parametric models, of course, can be faster to use, the disadvantage of this is that they can make strong assumptions about the data, usually assumptions of linearity or assumptions that the data follow certain probabilistic distributions. So another disadvantage that we have pretty much discussed about KNN is that it is usually difficult to run KNN in high dimensional spaces. And that is because KNN, the cost of computing the distances over high dimensional spaces can be pretty high. And also it is very difficult in high dimensional spaces to have enough data so that we can get a fair representation of our space, so that we can find an adequate number of neighbors to a test sample. So in high dimensional spaces, there might be cases where the nearest neighbors of a test sample might actually not be as close as we think. And essentially, that is the idea about cares of dimensionality, meaning that pretty much all intuition fails in higher dimensions, and there is a risk of having classifiers that are harder to generalize and harder to actually approximate a target function. And specifically KNN, because it relies on having enough samples to represent an area of a larger dimensional space, specific KNN is very prone to higher dimensions. So of course, the good thing about KNN is that there are theoretical guarantees that KNN actually works. So we're not going to go into these theoretical guarantees into very much detail here. However, there is something that is called expected conditional risk. And the expected conditional risk essentially reflects the error of a classifier given the labels that we have. So essentially this function here corresponds to the probability that we have a labeled sample belonging to the class 1 and the fact that our classifier has wrongly classified this test sample as belonging to class 0, and the corresponding expected conditional fault for a sample belonging to class 0, while the classifier has actually decided that this sample belongs to class 1. So this expected conditional risk can be actually very useful when we are trying to design theoretical guarantees for our algorithms. And what this is very much related to is what we call a Bayes optimal classifier, which reflects an optimal classifier that always yields the lowest expected conditional risk. The Bayes optimal classifier, it's theoretical and it's not computable, as we usually do not know the real distribution from which our data came from. However, the Bayes optimal classifier is a very useful tool for conceptualizing and formalizing certain aspects of our algorithms. So there is a theorem that basically says that the optimal conditional, that the conditional risk of the KNN classifier, of course, is greater compared to the risk of the Bayes optimal classifier, just because this is an optimal classifier, but there is an upper bound limit to this risk that depends on the risk of the Bayes classifier. So what this says is that while KNN is not the ideal classifier, it is all actually guaranteed to approach the Bayes error rate under ideal conditions. So in short, it seems to do a reasonable thing. Finally, if we were to summarize advantages and disadvantages of the k-nearest neighbor classifier, potential advantages would be that it is a very simple and easy to implement classifier. It's very intuitive, therefore we can actually make some sense out of our data. And also there are theoretical guarantees that it works, which is very important. However, we also have a good set of disadvantages. First of all, it can be computationally expensive for large data sets because we need to compute the distance of each test sample with all our training samples. We need to keep our training data in memory or to transfer back and forth our training data from between different memories, which this can be also very computationally expensive. Choosing the right hyperparameters, including the right number of nearest neighbors for our problem, sometimes can be tricky. And also KNN can be sensitive to noisy features, just because each of the features, if we are using Euclidean distances, for example, contributes in the same proportion to the evaluation criterion that is being used to find the k-nearest neighbors. And of course, another important disadvantage of KNN is that it does not perform well on higher dimensions, just because it's usually very difficult to obtain dense spaces in high dimensions. So with that, this will be the end of the first part of the KNN. And if you're interested in this, please look at the next videos for more practical applications of KNN.